There are over 500 solar systems in the entire Milky Way, our solar system being one of them. It was created 4.5 billion years ago, and it's located in the Milky Way's Orion star cluster. Only 15% of the star in our galaxy has planetary system. One example is our Sun, having 8 planets revolving around it. We can categorize these planets into 3 types. The first kind being relatively small terrestrial planets such as Mercury, Venus, Earth, and Mars, which primarily made out of rocky material. The second kind is Jovian, which describes the gas giant Jupiter and Saturn. Lastly, there are ice giants like Neptune and Uranus. But how can we access such an information while we are living on planet Earth? This kind of information gets collected by different agencies that specialize in exploring boundaries beyond the Earth. One of the most prominent agencies would be NASA that we all know. NASA has been operating on many missions to explore our solar system in order to expand the knowledge. As simple as it sounds, they have to consider quite few aspects for each mission, such as concrete objects and duration of their mission, and more technical aspects focus on use the technology. We will now take a closer look at one of the NASA's extraordinary mission, which is New Frontiers program. The New Frontiers program is a serious space exploration mission conducted by NASA to further understanding of solar system. There are currently 3 missions in progress and 1 in development. New Horizon, Juno, OSIRIS-Rex, OSIRIS-Apex, and Dragonfly. Consequently, all of this mission pursues very different goals. In order to understand each of them, let us dive deeper into detail of their key aspects and technologies.
First, let's jump from our planet to the outer solar system. Pluto, which used to be the 9th planet of our solar system, is a dwarf planet located farthest away from our Sun. However, Pluto is not considered a full-size planet anymore because it does not meet all the criteria set by the International Astronomical Union. It defines a planet as a celestial object that orbits the Sun, with a spherical shape due to its own gravity, which has cleared its neighboring region of other objects. While Pluto meets the first 2 criteria, it fails to meet the third one. There are still many asteroids and space rocks along its flight path, which ultimately resulted in the loss of Pluto's planet title in August 2006. Despite its category, in the public's eye, Pluto remained being quite mysterious. Even the renowned planetary scientist Alan Stern comments on its perception with the words,
"As a planetary scientist, I don't know what else to call Pluto. It's big and thousands of miles wide."
Adding to this quote, it is important to understand that one of the best pictures taken of Pluto before 2015, which was available to humans, was this right here. While many space probes have been sent out to the planets in our solar system, there was no exploration of the dwarf planet due to its far distance until 2006. This was about to change as the New Horizons mission started with Alan Stern as its principal investigator. To this day, this mission allowed us to upgrade our image from Pluto from this to this picture, which was taken by the respective spacecraft in 2015. To take amazing pictures just like this and to collect data of the far dwarf planet, New Horizons carries 7 scientific instruments. Let's begin with the first instrument, ALICE. ALICE is a special imaging telescope and spectrometer. As the word spectrometer will be mentioned quite a few times in this video, we are going to explain how it generally works. Similar to a prism, it separates light into its different wavelengths, but more advanced. In addition to that, spectrometers can measure and analyze the intensity of different wavelengths. During New Horizons mission, ALICE does exactly that, but focuses on ultraviolet signatures of noble gases and even allows the detection of water, carbon monoxide, and carbon dioxide. Together with ALICE, a second spectrometer called RALPH helps with the characterization of Pluto's atmosphere. In contrast to Alice, Rolf is equipped with black and white and color imagers, as well as an infrared spectrometer. It captures high-resolution images to create detailed maps of Pluto and its moons. The last optical instrument is called LORRI, which stands for Long Range Reconnaissance Imager. It is a telescope with a high-powered camera that captures detailed grayscale images of Pluto's surface, detecting clouds, hazes, and even providing snapshots of the surface activity. But let's go back to Pluto's atmosphere. For that, we have another instrument called the Radio Science Experiment, which is part of New Horizons' telecommunications system. It measures how radio signals bend as they pass through the atmospheres of Pluto and its moon, Charon, helping scientists determine their atmospheric composition and temperature. But it's not just Pluto itself that plays a role. The Student Dust Counter, now developed by students, counts dust particles in space that New Horizons encounters on its way to Pluto. When a dust particle hits the instrument, it generates a signal registered by integrated sensors. These signals allow calculations of the particle's mass and speed, providing insights into the composition and dynamics of the outer solar system. Similarly, Pepsi gathers data on not dust but atoms escaping from it. No, wait, that's a drink Pepsi. For the detection, however, we need the Pluto Energetic Particle Spectrometer science investigation. The discovered atoms are most likely charged through sunlight or interactions with particles from the solar wind, allowing them to move away from Pluto. Solar wind describes a stream of charged particles that constantly flows from the sun in all directions, about 1 million tons per second. Researchers then can investigate in which way energetic particles are accelerated by this force and Pluto's resulting loss of particles. Focusing more on the relevant forces, the Solar Wind Around Pluto instrument analyzes the characteristics further by measuring the particles of the solar wind through analyzing the mass and energy as they collide with its integrated sensor analogously. With this packed set of instruments, New Horizons was specifically designed to withstand the cold, low-light conditions of Pluto while being able to study them more closely. After its launch in 2006, New Horizons reached the Moon in just 9 hours. A year later, it used Jupiter's gravity to gain speed, flying at 50,000 kilometers per hour for 8 years towards Pluto. This boost, called a gravity assist, is when a spacecraft flies close to a planet to gain extra speed from the planet's gravity, a technique used in many space missions. Because of its speed, New Horizons couldn't slow down to orbit or land on Pluto, so it was designed as a flyby mission, passing the dwarf planet once and capturing amazing images. These images revealed a diverse landscape, including mountains, glaciers, dunes, and possible ice volcanoes. One of the more major discoveries, for example, was the 1,000-kilometer wide Sputnik Planitia Glacier, composed of frozen nitrogen. In January 2019, New Horizons proceeded its travel to a distant space rock known as Arrokoth, which is a peanut-shaped object in the outer solar system, located about 1 billion miles more distant than Pluto, making it the farthest place ever visited by humans. Since Arrokoth's double structure has remained unchanged since its formation, it allows conclusions to be drawn about the accretion processes in the early solar system. All the data New Horizons collects is transmitted back to Earth via radio, receiving commands and sending status updates through NASA's Deep Space Network in return. However, this happens with a low data transmission rate, much slower compared to typical internet speeds. Nevertheless, despite facing challenges like the slow data transmission and far distances, New Horizons significantly expanded our understanding of the outer reaches of our solar system and can be deemed as a successful first mission of the New Frontiers program.
In August 2001, NASA's spacecraft Juno began its long journey to the largest planet in our solar system, Jupiter. Jupiter is a colossal gas planet and it's about 318 times bigger than Earth. But why are we suddenly investigating in Jupiter? Like the other New Frontiers mission, Juno's aim is at improving our understanding of the solar system by studying the gas giant Jupiter, its origin and evolution. Juno's instruments have allowed us to explore Jupiter's chaotic atmosphere. They reveal the complex weather pattern, magnetic and the gravitational field, or even the depths of infamous Great Red Spot. This is done by orbiting over Jupiter's pull, which allowed Juno to capture incredible view of massive cyclones, stunning auroras, and much more, all while surviving extreme condition and high level of radiation. Images like this are taken with the help of Juno's array of high-tech instruments, which have allowed us to uncover some of Jupiter's secrets. Let's just start with our first instrument, the microwave radiometer. It dives deep into Jupiter's atmosphere to measure the water and ammonia levels and map the temperature profile. By mapping these profiles, the microwave radiometer helps us to understand the planet's atmospheric composition and weather patterns. Information about these characteristics is complemented by Jovan infrared auroral mapper, which capture infrared images of Jupiter's auroras. Similar to auroras on Earth, they are bright display of light near Jupiter's poles created by two forces: the solar wind and Jupiter's magnetic field. The solar wind refers to energy from the sun consisting of charged particles which are continuously released. These particles, in combination with Jupiter's magnetic field, collide with gases in the atmosphere, resulting in a beautiful auroras. Furthermore, Jupiter's magnetic field is precisely analyzed by the magnetometer on the Juno spacecraft, which allows scientists to infer detail about the planet's internal structure. This includes the composition and state of its core, as well as how the movement of liquid metal within the core generate magnetic force and influence the planet's overall dynamics. And additional to the analysis of Jupiter's auroras, Juno uses the Jovan auroral distribution experiment JADE and the Jovan energetic practical detector instrument JEDI. These instruments complement each other as they measure higher and lower energy ions and electrons respectively. The resulting data is used to characterize the polar magnetosphere of Jupiter and its aurora's origination process. In cooperation with JADE, Juno is equipped with ultraviolet spectrograph which captures ultraviolet light from Jupiter's poles. Together, the collected data of the UV emission and high-energy particles measured by both instruments can be synthesized. With this, scientists aim at learning more about the source of Jovan magnetic field. On top of that, the radio and plasma wave sensor listen to the radio emission and particle movement in auroras. Analyzing these waves help our understanding of the interaction between Jupiter's magnetic field and the charged particle from the solar wind. Additionally, Juno possesses the so-called Stellar Reference Unit. It's a star camera which is shielded against Jupiter's extreme radiation environment. It's bombarded by high-energy particles. However, only those with the highest energy can still reach the sensor on the inside. The signature from high-energy electrons and ions hits appear as dots, squiggles, and streaks in the SRU images. These images are then processed to extract radiation-included noise signature to profile the radiation levels, which Juno encounters while closely flying by Jupiter. In contrast to the other instrument, the gravity science instrument SID uses a different approach. It consists of different components which measure the spacecraft velocity over time by detecting minute changes in the radio frequency. This is done by using not only the spacecraft itself, but also additional hardware on Earth, enabling scientists to determine Jupiter's mass, variation, and gravity effect. The last instrument is the Juno Cam, which is a visible light camera with a resolution of 15 km per pixel. It uses the push broom method, which captures the pixel of entire line at the same time, like a broom, and creates a planar sense by joining the individual lines together. Different from the other instruments, the resulting images are not only useful for scientific study but also for engaging the public as they are published into the official NASA archive. Together, these instruments have transformed our understanding of the giant planet, making the invisible visible and the unknown known. In August 5, 2011, Juno launched from Florida, abroad on an Atlas V rocket at noon, embarking on a 5-year journey to Jupiter. To gain the necessary speed to reach Jupiter, Juno used the engine head back toward Earth for gravity assist in September 2012. Returning 26 months later, Juno flew past Earth using on the planet gravity like a slingshot to boost speed, giving it enough energy to travel Jupiter. These clever maneuvers allowed Juno to reach Jupiter faster and more efficiently. In January 2016, Juno began its final approach to Jupiter and recorded a time-lapse video of Jupiter and its moons from over 4.8 million kilometers away. By July 2016, 5 years after launch, Juno arrived at Jupiter, traveling at 208,000 kilometers per hour. Juno performed a careful maneuver to slow down and positions itself 78,000 kilometers away, capturing stunning images of blue cloud structure and giant storms of Jupiter. After its arrival, Juno has been orbiting the planet, sending back thousands of photos and 100 gigabytes data. Its mission, initially planned to end in July 2020, has been extended, and it will continue through at least September 2025. When Juno's mission concludes, it will perform a controlled deorbit into Jupiter's atmosphere to prevent the pollution of its moon. For now, Juno's instruments continue to operate normally, providing invaluable data about the largest planet in our solar system.
Okay, let's move on to the last active mission. Unlike the previous ones, whose goals were to explore planets and moons, the space probe of the following mission will explore asteroids. An asteroid is a small rocky object that orbits the Sun. Smaller than planets, most asteroids are located in the asteroid belt between Mars and Jupiter. They are thought to be the remnants of the early solar system, offering valuable insights into its history and formation. Hence, our mission takes a closer look at examples of the kind, starting with Bennu, which is known for being a carbon-rich asteroid that is roughly half a kilometer wide at its equator. More than 4.5 billion years old, Bennu's composition was likely established within the first 10 million years of our solar system's formation. Originally formed in the main asteroid belt between Mars and Jupiter, Bennu has since traveled closer to Earth. This ancient asteroid may contain organic molecules similar to those that could have played a role in the origin of life on Earth, making it a valuable target for scientific studies. This is done by collecting data via the spacecraft OSIRIS-Rex. What differentiates this mission is that rather than just orbiting around the asteroid, it is the first US mission that will actually collect a sample of Bennu's surface materials and return the sample back to Earth. In order to understand how that works, let's break down its name and its goals and connect them to the instruments serving as the tools to achieve these goals. Naturally, the O stands for Origins, referring to the origins of the solar system. For that, the OSIRIS-Rex camera suite is a collection of 3 high-resolution cameras that capture Bennu's surface and surroundings. The first camera, Polycam, is a high-resolution camera used for close-up imaging of Bennu's surface. The second camera, MapCam, is a medium-range camera that captures images to create global maps using various color filters. Lastly, the SAMCam is a sample acquisition camera that helps with guidance during the sample collection process. Moving on, the SI stands for the spectral interpretation, which describes the analysis of the asteroid using spectroscopy. This is done by the instruments OTAS and OVIRS, which stand for the OSIRIS-Rex Thermal Emission Spectrometer and the Visible and Infrared Spectrometer. These spectrometers focus on infrared wavelengths, providing crucial information about minerals and temperatures. This helps creating global maps and identify potential sample collection sites for OSIRIS-Rex to land on, adding to the information provided by the mapcam. With this, scientists can gain insights into Bennu's composition, which is why the name includes RI for the identification of resources, such as water or metals, and its geological history. Here, a third spectrometer comes into play. The regolith X-ray imaging spectrometer identifies the elements on Bennu's surface and measures their abundance. It works by detecting X-rays that are emitted when solar X-rays and solar wind interact with the asteroid's surface. These interactions cause atoms on Bennu to release their own X-rays, a process called fluorescence. REXUS captures these X-ray emissions to map the elements present on the asteroid. Since analyzing resources requires data of the surface, REX stands for Regolith Explorer, referring to the study of the surface material of the asteroid. For this, the OSIRIS-Rex laser altimeter is a scanning LiDAR instrument. It sends laser pulses to Bennu's surface, which then get reflected back to the spacecraft. By measuring the time it takes for the pulse to return, OLA calculates the distance to the surface, allowing to create detailed 3D maps of Bennu's topography. However, the part of the OSIRIS-Rex spacecraft that makes the mission so exciting is the touch-and-go sample acquisition mechanism, or TACSAM. This isn't just an instrument, but a robotic arm designed to collect surface material from the asteroid. The arm is about 3.4 meters long and has 3 joints, allowing it to precisely extend and touch the asteroid's surface. At the end of the arm is the sampler head, which is used to collect regolith from Bennu. When the spacecraft touches the surface, it releases a burst of nitrogen gas to stir up the loose material. The gas causes the dust and small rocks to rise into the sampler head, where they are trapped in a porous surface. Once the sample is collected, the arm retracts and the material is stored in a sample return capsule for transport back to Earth. The arm also works with cameras and sensors, like the SAMCAM, to capture images and ensure the collection process goes smoothly. That being said, we have skipped the S in the acronym, because instead of focusing on Bennu itself, the main concern is the potential risk Bennu poses to Earth as it advances towards our planet. This results from its orbit being more unpredictable than that of a planet, as it is influenced by various gravitational forces of other space objects, which means that its approach to our planet could lead to a potential collision. Equipped with advanced instruments, OSIRIS-Rex was launched on September 8, 2016, and arrived at the asteroid Bennu 2 years later, in December of 2018. As the spacecraft approached Bennu, the mission team selected a sample site called Nightingale, located in a 140-meter wide northern crater. Due to the crater's young age, its regolith is freshly exposed, providing a relatively smooth surface with fine-grained material ideal for sampling. This led to a successful sample collection in October 2020, which was safely returned to Earth on September 24th in 2023. As a piece of side information, TACSAM was actually designed to collect up to 3 samples, but on its first attempt, it gathered so much material that no further attempts were needed. The sample was even larger than expected, providing a wealth of material for study. However, OSIRIS-Rex did not return to Earth with the spacecraft itself, but rather than that, it dropped off the capsule containing the sample in the Utah desert. After the sample delivery, OSIRIS-Rex, now renamed to OSIRIS-Apex, departed again to continue its next mission, exploring a second asteroid, Apophis. Apophis is currently on a trajectory that will bring it within 32,000 kilometers of Earth's surface in 2029, closer than our highest altitude satellites. In conclusion, the OSIRIS-Rex and OSIRIS-Apex missions will represent significant advancements in the space exploration. As we continue to explore the space, these missions remind us that even small celestial bodies like asteroids have much to teach us.
The next planet mission in NASA's exploration of our solar system takes us back from the distant rings of Pluto, Jupiter, and Bennu to the worlds of Saturn, especially one of its most prominent moons, Titan. Titan stand out as a prime target for scientific studies due to the unique characteristic it has, which were discovered by a prior mission focused on Saturn itself and its potential for harboring life in the future. Images of Titan's surface reveal similarities to Earth's early days, such as vast expanse of sand, dunes, and even rivers and lakes, earning Titan the label of an ocean world. Also, it has seas of liquid ethane and methane, which is the main component of natural gas. These gases combined with Titan's climate are able to form clouds and rain, just like water does on our planet. However, compared to the rain on Earth, Titan's rays fall much slower. This is influenced by a denser atmosphere in combination with Titan's gravity, which is approximately 1/7 of our gravity. Further images hint at the existence of cryovolcanoes, which are defined as a phenomenon in which ice acts like rocks and water, just like lava. Scientists speculate that these volcanoes continuously supply Titan's atmosphere with methane, which otherwise would have been exhausted long time ago. As a result of collecting all this data, assumption about various characteristics of Titan, such as cryovolcanoes, has been made, though scientists now aim at verifying them. This can be quite challenging to the dense atmosphere and generally distance to Earth, which make it hard to study a Titan from far. Despite that, Titan remain quite interesting due to its potential to harbor life in the future, especially as it's not a planet but a moon. Therefore, the new Frontiers mission, Dragonfly, has been designed to specially study Titan. Comparable to the mission of OSIRIS-Rex, Dragonfly will focus on Titan's chemical composition by gathering samples of muco, which are collecting using a drill. Afterward, a chemical analysis process is used to gain further information about Titan's surface. With its launch planned in 2028, we hope that Dragonfly can provide humanity with more insights about our solar system. Go Dragonflies!
After everything we have seen in this video, NASA's New Frontiers missions have expanded our understanding of the solar system in impressive ways. Let's have a quick recap. In 2006, the New Horizons mission was launched, the first spacecraft to explore Pluto and the Kuiper Belt. After nearly a decade of travel, it reached its destination in 2015, delivering stunning images and valuable data about the complex geological structures of the dwarf planet. The second mission, Juno, was launched in 2011 to study the gas giant Jupiter. Since 2016, Juno has been orbiting the largest planet in our solar system, providing previously unknown insights into its atmosphere, magnetic field, and internal structure. Juno has shown that Jupiter is much more complex than previously thought, with chaotic weather phenomena and a surprisingly asymmetric distribution of mass and energy. OSIRIS-Rex, the third mission, launched in 2016 with the goal of exploring the asteroid Bennu. After 2 years, the probe reached its destination and collected a sample from the asteroid's surface in 2020. This sample, which arrived safely on Earth in 2023, will provide us with unique insights into the early building blocks of the solar system and possibly even clues to the origins of life on Earth. The future of the New Frontiers initiative looks just as promising. Dragonfly, the fourth mission, will head to Saturn's moon Titan in 2027. Using an innovative rotorcraft, it will explore the surface of this fascinating Earth-like moon to learn more about its chemistry, meteorology, and potential conditions for life. We look forward to the new insights we will gain from the current and future missions. The exploration of the universe is only just beginning,
And with each new discovery, we come closer to answering humanity's greatest questions about space.